Okay, so I made a new inverter that I'm going to be using this as the step-up transformer. And so here's my old one over here, and I have these solid-state relays, 2 here and 2 here. These are pretty slow, plus it's switching at the high and the low at the same time. It's called an H switcher. And so what I'm going to do now is I have these MOSFETs here and little 4421 chip, and this can switch very fast. And what I'm going to do is it's going to be an inverter with a 12-volt battery here and a 12-volt battery here, 2 batteries, and this will switch in going one way into the primary, and this one will switch battery number 2 the other direction. So there'll be 12 volts pounding this primary here. It's about 0.08 ohms, and it's 16 parallel wines, and I split them into a cluster of 8 and a cluster of 8 for the in, and for the out a cluster of 8 and a cluster of 8, and I run a cluster of 8 in series into the other cluster of 8, so it's like a bifilar coil, except instead of 2 wires, it's a cluster of 8 parallel wires. So that's the primary. These are 23 ohms each, so there's your step up in voltage. And when I when I used this, getting blasted with 12 volts going alternating directions with this, I had 123 volts on the output of this from the 2 secondaries in series, and that's without a load. So one thing I did is I made these little foam, because it's easy to work with, so I can finely adjust, make sure the 90 degrees. Okay, so here's a little timing magnet. Here's a little timing magnet. So it goes like this. Let's say it goes around this way. It goes bang, this one fires. Then it goes bang, that one fires. So there's your alternating DC. And then this one comes around, bang, this one fires. And then that one fires, bang. So that's how you get AC from DC. And before, it wasn't exactly perfectly like each pulse was exactly in the middle of each one. So I have this, so when it's running I can adjust it and make sure it's perfectly even when the pulses hit. I tested the motor. It draws 10 milliamps at a very slow speed, and if you crank it all the way up, it goes to about 60 milliamps. So it doesn't draw too much. So each one is going to have its own 9-volt battery supplying power to the chips and the MOSFETs and the Hall effects and everything. And then the battery is going to be attached to the drain, you know, and the source to knock it into the primary of the bit transformer. And also, this is just like a DC pulse motor, really. And so there should be some good flyback, and I can have a cap and a steering diode collecting over here, a cap collecting it, and I could do the same thing over here. And I have an idea, if instead of a single MOSFET, I had a bidirectional MOSFET. That's a pair of two MOSFETs kind of back to back, where the gate and the source connect together, and the drain of MOSFET A and the drain of MOSFET B is where your switching is. And this is how you can switch AC with MOSFETs, is you connect them bidirectionally. So what I'm thinking is perhaps a way to get the reactive power, like when you get a really big phase shift going on with a transformer, like maybe over 90 degrees type of thing. And so it starts going into the negative, and so it's supposed to be returning power to the back to the grid if you're using the grid. Now, if I had bidirectional MOSFETs switching in and a steering diode on the drain, maybe on both drains, maybe have a full wave bridge rectifier AC legs across it, and have that filling a capacitor, that might be all you need to gather up the reactive power coming back. Maybe. That'll be an experiment later. I'll have, instead of a single MOSFET, I'll have two. I'm sure the steering diode's going to be filling up the cap pretty good. And I could have a second battery and do the BiTT battery charging thing with the flyback also. So, hopefully this thing's not going to poop out like it, you know, half speed. In a video before, I showed how when you get up to high, like I'm making like 102 volts here or something. I think it was 64 volts I was making here, coming out of the secondaries of the primary, and the primary is being pulsed by an inverter. It was this one though. And then at a certain frequency, a certain RPM and speed, instead of the volts climbing and climbing with more frequency, it hits some sort of threshold or a plateau where it won't go any further, and it starts to actually drop when you get to a higher frequency. And I believe that's because the switches are too slow here. So that's what I hope to make work good, by having a MOSFET and a MOSFET and its own battery and its own battery. What would be fun is to, instead of filling a cap, you actually slam the back EMF spike, the flyback spike, into the opposite battery, and do the same over here, send it over here. I think there's going to be a problem with a common ground though, so I might have to have another switch to have the ground disconnected on the on one side of it, but I'm not sure about that. But for now, I'm just going to fill an external cap with the flyback back EMF, as is normal. So I'll be putting a little white strip here so I can check RPMs with my RPM meter. I found it. So I can see what the frequency is very quickly. When this goes 1800 RPM, it will be 60 Hertz. If it's going 900 RPM, it will be 30 Hertz, because it's like a 4-pole AC motor, more or less. So that's going to be something to do. Okay, I'm going to work on this transformer here, the one with the thick laminates. The voltage looks kind of funny. It's wider and more rounded on the positive half, and it's narrower and not as sine wave on the negative half. So that means when you're checking for phase shift, it can really throw you off because it's not a perfect sine wave. So I don't know why that's happening. I'm guessing perhaps the flow through one half is not as good as the other half. This has a three-phase transformer. It's actually called a line reactor, and so it has a big E core, you know, and you can see the core going across. I call it a cross beam. And then, so this is all solid on this half. There's not going to be any problem with magnetic flow on the transformer on this half of it. But on this half, this blue beam right here, this laminate bar here, going across, this actually comes off, and right now it's super glued on there, and I used to have a bunch of wire ties like here really holding it on there snug and tight, but I just took those off because I'm gonna probably take this shunt bars off and also take this off. It makes it easier to wind when they have these, so you can, they aren't attached, they aren't solid, because you can, now you have these three legs exposed and you can wind them easy. And because it's a line reactor, there's usually a plastic strip, like maybe 2 millimeters thick, that goes all the way across, so it creates like an air gap, like about this big. And that's the way they work. I think it's supposed to only let the spike get through, so it works kind of like a spike filter. And that's the way line reactors are. They're very similar to three-phase transformers, but there's this plastic strip there. And my first one of these I built, it not only had a strip, but it had a ridge, a metal ridge that made it so the crossbar didn't really sit flat, and it would kind of rock. So I had to file that down really flat. And I have a feeling that why the voltage is weird now is because this half is not as tight as this half. You see how the laminates fit here? You want a really tight fit there. There's kind of a gap there, so So I'm going to be taking this, I'm going to test this first, and then I'm going to probably take this off and file it some more, make sure it's really flat. Also, another thing is there's the two secondaries, and they should have the exact same voltage. If you just check the voltage off of this secondary and this secondary, they should be exactly the same. But this, when I checked it, one was higher voltage than the other. So that kind of indicates that there's something where kind of making it bias to one side. So it's either the secondaries are causing this weird voltage. If you look at the video before this one, you can see what I'm talking about. The amps is angular. It slopes to the right, but the voltage is straight up and down, but it's funny looking. It's narrow on the bottom and wider on the top. So it's either the secondaries aren't balanced, or I have a feeling it's these shunt bars are not balanced. In fact, I bet you it's this cross beam. I bet you the shunt bars are okay, but this cross beam is probably not sitting right on this. Maybe that's it. I don't know. But I'm going to work on this. I checked the impedance, and they're all good. There was one of these wires where I connect them all series 80 was a little funny, and I had to resolder it, but that wouldn't cause the weird looking voltage anyways. So okay, so this is my projects coming up, and thanks for watching.